Hello, my name is Leo. Today we are going to talk about FLOPS. What is FLOPS? FLOPS stands for Floating Point Operations per Second. There is also term FLOP, which is in some cases used just as an abbreviation of FLOPS and generally in FLOP count of operations executed by a computer program. So what is FLOPS? It is measure of computer performance through its computing ability, since every computer has a certain limit of finite precision. It is measured in metric system where 1 kilo is 1000, 1 mega is 1 million and so on. So we have kiloflops, megaflops, gigaflops, teraflops, petaflops and so on. These greater measuring units, such as mega, giga, tera and peta, flops are usually used for expressing performance of more powerful computers or supercomputers and in parallel processing. Where is it used? It is very useful in scientific calculations where very accurate calculations are of great importance. Just because of this fact, there is used FLOPS rather than just number of instructions per second, IPS, which is a measure of computer's processor speed. There is also a similar measure to FLOPS, which is MIPS, which stands for millions of instructions per second, and JIPS, billions of instructions per second, and KIPS, thousands of instructions per second. While FLOPS primarily measures supercomputer performance, MIPS measures integer performance of a computer. Just for a comparison, a supercomputer is a computer with a much higher level capacity for computations than normal general-purpose computer. FLOPS is used for representation of basically two types of numbers. First type are fixed point numbers, actually integers. When a computer deals with these numbers, decimal points are not used because decimal point is fixed at the end of the number. These numbers can be positive or negative integers in some range. For example, 8-bit computer will have 2 to the 8th power possible bit array combinations, which is 256 combinations. The second type are floating point numbers, which are real numbers, usually very small or very big ones, and also they are irrational numbers, which are numbers with infinite number of decimals which don't have to be repeated, such as in number pi. Interpretation of floating point numbers is similar to the scientific notation, where there is base of 2 raised on some power instead of base of 10, which is normally used since we usually deal with decimal system. The widely accepted standard for this interpretation is ANSI IEEE standard 754. It also includes various degrees of floating point number precision, such as single precision for 32-bit numbers, double precisions for 64-bit numbers, and extended precision for numbers longer than these. So the exponent in floating point notation is what enables much larger dynamic range of numbers, which are possible to be represented according to the mentioned IEEE 754 standard, which is again very important for measuring different parameters in numerous scientific calculations where we deal with either very small or very large numbers whose range cannot be predicted in advance. How to convert from decimal to binary floating point number? To represent a real decimal number as a floating point binary number, we have to know rules of IEEE 754 standard, but first know how to convert numbers from decimal to binary number system. Let's do this on the next example of number -23 but 0.65. First, take the integer part of the number, it's 23, and convert it into binary. It's 10111 in binary system. For now, don't pay attention to the sign, which is in this case negative. For this conversion, you can watch the video on number systems. The next part is decimal part of the number, which is in the example 0.65. To convert it into binary number, first we have to multiply decimal part 0.65 by 2, and then we get 1.3. This 1 in 1.3 is going to be the first decimal in binary number. Next step is to take only this decimal part of gotten number, so we take only 0.3 from 1.3 and write it on the left hand side just below 0.65. What we have to do now is actually the same as we've done for 0.65. We multiply the number 0.3 by 2 and write the result on the right hand side of the vertical line next to 0.3. Then again take only the decimal part of 0.6, which is 0.6, and now integer part of 0.6, which is 0, is going to be the second decimal in the binary number. You can ask yourself until when we are going to repeat these steps. The answer depends on type of floating point number. If it has decimals which do not repeat in any particular pattern, meaning they do not have array of digits which periodically repeats, it will be rounded, since there is limited number of bits reserved for it, depending on its precision, if it's single, double or extended. However, the second possible outcome is that it's going to be a number with finite number of decimals or a number with infinite number of decimals but with a repeatable pattern. In this example, we'll have the latter case. We can see that the integer as well as decimal part of number on the right hand side begins to repeat in certain pattern. The decimal part goes in this way: 3, 6, 2, 4, 8, 6, 2, 4, 8, 6, and so on. Here we can see a pattern of period of number 6, 2, 4, 8, which begins to repeat to infinity exactly after the first number in the sequence, number 3, and then we have 6, 2, 4, 8, 6, 2, 4, 8, and so on. These periods are framed with green frames. The same is with integer parts of these numbers. They go in this way: 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, and so on. Here is the period of constantly repeating 1, 0, 0, 1, which is also framed with green frames. Finally, the binary number equivalent to 0.65 is 0.10, 1001, 1001, with the period of 1001 going to infinity on the decimal side of the number. So we have to read only the integer parts of the numbers gotten on the right hand side in downwards direction. By the way, we can also see on this example the opposite way between conversion of integer part of a given number shown on the left hand side and conversion of decimal part of a given number shown on the right hand side. While in integer conversion we divide the numbers on the left hand side of the vertical line to get those on the right hand side, in decimal part conversion we multiply rather than divide numbers by 2. Also, in integer conversion the binary number is read in upwards, however in decimal part conversion in downwards direction. Finally, we can write the conversion. This binary number is sum of its integer and decimal parts, so we have to do the next. Don't pay attention to this minus sign at the moment. And here we have this conversion. Floating point notation, so for 32-bit long array. How is computer going to represent this number in 32-bit space, which is enough for single precision using IEEE 754 standard? You can see here this space of 4 bytes, each having 8 bits, and each of them will have value of either 0 or 1. To do this, we have to first write the number in scientific notation, but using the base of 2 rather than the base of 10, since computer represents number in binary rather than decimal form. We have to get the integer part of the number to be 1. For that, the decimal point has to be shifted for 4 places left, which means we'll have to multiply the row number, the new number by 2 on the 4th power to get the original number. And we can see that here, so in this conversion, 1 point, and then we have this decimal part in binary form also. When we've got the number, we have to determine the next, its sign, exponent, and mantissa. Sign can be either plus or minus, if a number is positive or negative, respectively. So the first bit is reserved just for the sign. If a number is positive, it will get the value of 0, and if it's negative, it will get 1. In the example, we have the negative number, so the first bit will get value of 1. Exponent in the example is 4, which is binary 1, 0, 0. The next 8 bits are reserved for exponent, but we won't have 0, 0, 0, 0, 0, 1, 0, 0 in binary, which is equal to 1, 0, 0 in binary. The reason is exponent bias, which was introduced so that both small and large values can be represented. Because of the bias, we have to add 127 in the case of single precision, so our exponent is going to be 4 plus 127, which is 131. As decimal number, it is this one, so 1, 0, 0, 0, 0, 0, 1, 1 as binary, so write it into this place for exponent. And it is also referred to as the characteristic of the number. The last component, called mantissa, is actually the decimal part of the number, which is reserved the remaining 23 places for. Before we fill out these 23 empty places, we have to be aware of what should be written first. Is the first part of the decimal part of the number, which is the part before the period, which is the sequence of repeating decimals. So first write 0, 1, 1, 1, 1, 0, and then the period 1, 0, 0, 1 to the end of the number. It's possible that the last time the period is written in, it won't be written to its last digit. So we have here 0, 1, 1, 1, 1, 0, and then we have the 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. So we have here. We can see we've had to cut the last period because we've begun to write already after the first digit 1 of the period 1001. The last thing is just to round the number. We know the next decimal of this number will be 0, which comes after the first 1 in the period 1001. Therefore 1 will be rounded to, because of 0 will be rounded to 1, so after it does not change after, because 0 is after the 1. In this video, you've learned what FLOPS is, why it is important especially in science, and finally, how floating point numbers are represented in computer. Thanks for watching and stay with us.